Okay, let's talk about integrals. Really, this is a triple in cylindrical coordinates. There's two ways to think about this. The first way to think about this is just replace dv, which we know as xy, dx, dy, dz, replace that with r, dr, d theta, dz. Again, the recurring thing in cylindrical coordinates is do nothing to z. So that dz is going to be the same. And the only thing that changes is dx, dy, changing it to dr, d theta, and that's just doing integrals in polar, double integrals in polar. Okay? And then you have to also change your limits to polar. So for example, if we had, I don't know, -1 to 1 minus square root minus x squared. Okay, I'm doing this down the unit circle, right? That's really what's going on here. So plus square root of 1 minus x squared. Then if you do polar, you have to change that to 0 to 2 pi and then 0 to 1. So that's what I mean by limits. So, and then once you do that, you'll end up with some integral. Now you'll have a theta, now you have an r, now you have a z, and you'll have your f of r cosine, r sine, z, and then you'll have your new dv, r dr, d theta, dz. So then you just do this as a triple integral in like as normal. You just do now that we've done the change, now you just evaluate this integral and crunch it out. That's what I mean. But there's a second way to think about this. Just do the z integral without thinking about it. And no conversion is necessary. So let me give an example. Let's do the triple integral of just z dv. And by the way, if you don't see a z here, then it's just a volume integral. And we know how to do volume integrals because you can either do them in polar coordinates or Cartesian. Polar's probably easier for these problems, but I'm just saying you don't need to know anything new to do volume integrals. That's old hat. You just use the base times height. So E here will be the region enclosed by z equals x squared plus y squared and z equals 4. So the first indication why cylindrical is that you should notice x squared plus y squared. If you see x squared plus y squared, think polar or cylindrical. Okay, so I would now draw this in the ZR plane. So if you put z on the y-axis and r on the x-axis, 4 I can draw pretty easily. And then the second one is r squared. So we draw r squared. And that, of course, will be r equals 2 for that intersection point. And we see that we can represent this as a graph of z as a function of x and y. So that means we can use it as our inner integral. Right? So that is to say we can replace this this integral over e, but using Fubini, we can now replace it over the base times z stuff. So the z range. We'll put a dz here, then we'll put a dA out here. Right, so this is actually, I haven't even used any polar cylindrical stuff yet. This is how we did Cartesian integrals. We always find graphs, and then we make those the ranges, and then those will be our inside integrals. So our z range, it's well, the lower is r squared, and the upper is 4. So I'm going to put those in my limits here. So r squared and 4. And, oh yeah, I forgot the integrand, so let me just write out integral over e of z dv. That'll be the integral over the base times the z integral. So r squared to 4 of z dz. Now dA is going to be on the outside. So what I'm saying is we didn't even need polar coordinates to get to this. We just need to do that z integral now. The only polar thing is that r squared is in the limits, but the limits are constants, right? We don't need to do anything with them yet. Okay, so I'm just going to select everything here. Or let me just rewrite it. So we have the base, then we have r squared to 4 of z dz, then we have dA. And what I'm saying is that that z integral is totally doable without polar. So no polar needed for yet. We don't need the polar coordinates yet, or cylindrical. So let's just do that one. This is 1/2 z squared from r squared to 4, so that's 1/2 16 minus r to the 4th. So now we get an integral over the base times 1/2 16 minus r to the 4th dA. This is now just an ordinary double integral over the base. If we go back to our little drawing, we see that the base is our r range. So if you want the base, just look at the r range. In this case, it was 0 to 2. So now you can use polar coordinates to do the double integral. And our theta range is just 0 to 2 pi, because theta does not appear anywhere. Okay, so our double integral now is, we have the theta part that goes from 0 to 2 pi, then we have the r part that goes from 0 to 2, and so then we have 1/2 16 minus r to the 4th, and then we have our dA, which is r dr d theta. Okay, and so this can be this, and then the rest is routine. It's just ordinary integration. Right, because there's no theta, so you can just integrate the theta to 2 pi, and then now we just have an integral in r. Okay, so that one will be straightforward. Okay, so if you see example problems where they want you to convert it to well, if they want to give you an integral and you think you need to use cylindrical coordinates, I would say just don't worry about it and just do that inner z integral first before doing polar, just to make your life less complicated. Okay, thanks for watching.